You use it to walk, to drive your car, to even just hold a pen. It's this incredible force that we rely on every single second of our lives, but you can't see it. So today, we're going to get to grips with the invisible power of friction.
We see signs like these all the time, right? Warnings about a lack of friction. Caution, wet floor, slippery when icy. We're constantly being told to be careful when friction decides to take a break. But honestly, how often do we stop and think about what this force actually is?
Because when you start to dig in, that simple resistance you feel when you slide a book across a table, well, it turns into a totally fascinating and complex story. So let's ask the big question. What is friction? For real? Now, we all kind of have a gut feeling for what friction is, but to really get to the bottom of this everyday mystery, we need to start with a clear definition. At its most basic level, that's all it is. When you try to move one thing against another, friction is the force that says, nope, and pushes back. Simple enough, you'd think, but the real question is why it pushes back, and why some things are so much grippier than others. So, how do we even measure this stickiness? I mean, it's not just some vague feeling. It turns out, scientists can actually put a number on it, which lets us precisely compare how different materials are going to interact with each other. And that number is called the coefficient of friction, which we represent with the Greek letter mu, or mu. So, a low mu means the surface is super slippery, like ice on steel. A high mu means it's really sticky. This one little number tells us a whole lot about how two surfaces are going to behave.
And what's wild is just how much this number can change. So, take a look. Steel on steel is about 0.4. But then you look at some precious metals, gold on gold is 2.5. And platinum? Platinum is a whopping 3.0.
Yeah, that's right, 3.0. That means platinum rubbing against itself is incredibly sticky. It has this huge resistance to sliding. But why? What is it about certain materials that makes them so much more resistant to moving than others?
Well, this points to a really cool general rule that comes from our source material. It turns out the coefficient of friction tends to be higher when you rub a material against itself, like steel on steel or platinum on platinum. It's like things just prefer to stick to their own kind. And that's our first big clue in solving this whole friction mystery.
To find the real answer, we've got to zoom in. I mean, way, way in. Because the true nature of friction isn't something you can see with your own eyes. We have to go down to the microscopic level. See, the key to understanding all of this is realizing that a surface isn't just some flat thing. It's a landscape. It's a whole world of its own, with peaks and valleys and everything. And here it is. This is the big reveal. To you and me, a piece of polished metal might feel perfectly smooth, but on a microscopic level, it looks like this, a rugged, jagged mountain range. So when you put two surfaces together, it's not the whole thing that's touching. Nope, it's just the very tips of these mountains crashing into each other. Okay, so if friction is really just these tiny mountain peaks grinding against each other, what is actually happening down there? Well, scientists have pretty much broken it down into two main causes, something they call adhesion and deformation, or a simpler way to think about it, sticking and plowing. So first up is adhesion. At the tiny points where those microscopic peaks make contact, the atoms get so close that they can actually bond together. It's wild. They form these tiny, temporary, cold welds. So the force of friction we feel, that's actually the force it takes to break millions and millions of these tiny welds as the surfaces slide past each other. Just look at this example. When a piece of steel is pressed into a softer metal, like indium, and then pulled away, it literally rips off some of the indium atoms that have welded to it. That's adhesion right there in action. It's pure atomic level stickiness. Then we have the second cause, deformation. You can think of this one as plowing. This is what happens when the peaks on a harder surface get dragged through a softer surface, digging grooves and literally pushing material out of the way. This one is less about sticking and a lot more about just brute force. So let's put them side by side. Adhesion is that atomic attraction, the cold welds. Deformation is the physical plowing. Adhesion is the main event when surfaces are really clean and smooth, while deformation really takes over when one surface is way harder than the other. The friction you actually feel is the sum of both of these incredible microscopic forces working together. So, after that crazy journey down to the atomic level, what's the big picture? When you get right down to it, is friction our friend or is it our foe? So here are the key things to remember.
First, no surface is truly smooth. They're all microscopic mountain ranges. The friction we feel is really a tag team of two forces: atomic sticking, or adhesion, and physical plowing, or deformation. And all of that complex action can be boiled down to one single number, the coefficient of friction.
And that kind of leaves us with one last thought. I mean, we spend billions of dollars fighting friction in our machines, trying to reduce wear and tear and make things more efficient. But without it, you couldn't hold a pen, your shoes would have zero grip, and your car's tires would just spin and spin. Which really makes you wonder, is this invisible, microscopic force ultimately working for us, or is it working against us?